All right, how's it going? Welcome back to another video here in the series on mechanics and relativity. We are still in the section here, the first section on Newtonian mechanics, and you'll see that there is a lot of writing behind me on the whiteboard, and all of the words that are here on the board describe a set of three laws known as Newton's laws. And Newton's laws we described as kind of these foundational principles which Newtonian mechanics lies on, kind of the fundamentals of Newtonian mechanics. And this was more or less the stopping point of the last video. Because if you remember, in the last video, we started by introducing these basic ideas in physics, like the notion of a particle, the notion of a reference frame, and then the Newton's laws was kind of the stopping point, right? And when we described Newton's laws, we did so in a very qualitative manner. And then that's why everything on the board here is in words. We said this is what Newton's first law is telling us, what the second and what the third law are telling us. And then we went through some examples kind of in words just to gain a sort of intuitive understanding for what's being said here, right? But as it turns out, there are more subtleties and more details that can be uncovered within Newton's three laws that we didn't get to in the last video, because I didn't want to put too much all into one video, right? But just to, I guess, as a very immediate example about how there is more to the picture than just these three laws right here, I want to first go back to Newton's second law and then point out something that we may or may not have noticed in the last video, but we didn't explicitly mention it, so I want to do that now. Newton's second law says that if we have a force acting on a particle, which we can denote with the uppercase letter F, so if a particle experiences a force, F, then that particle is going to accelerate, and the acceleration is going to be proportional to this force right here. So if we describe the acceleration of the particle with the letter A, we can say that the acceleration that a particle experiences is proportional, it's supposed to be the proportional sign, to the force that is exerted on it. Okay. So this is what Newton's second law more or less was telling us. But what we didn't explicitly mention is that Newton's first law, so not the second one, but the first law, can actually be thought of as kind of a special case scenario of this second law right here. So let's understand why that's the case. And then we might also be asking, well, if Newton's first law is just a special instance of the second law, why do we have a first law in the first place, right? And we're going to get into that in this video. But just really quickly here, Newton's first law tells us that unless a particle is acted on by a force, this is what it's going to be doing, okay? So the second law says if you have a force, whatever the value of F is, the particle is going to accelerate and the two are going to be proportional. The first law says, well, what happens in the case where F is not just any number, or it doesn't just have any value, but it's exactly zero? What happens if the force is zero on the particle? Well, in the case where the force is zero, then the particle is either going to remain at rest, if it started at rest, or it's going to be moving uniformly in a straight line. It's going to be moving in a straight line at a constant speed. And we talked about this in the last video, that moving at a constant speed in a straight line is just another way of saying that you're not accelerating, right? You're not speeding up, slowing down, or changing directions. So really, what Newton's first law is saying is that if your force is zero, then your acceleration's zero, right? And we might not have noticed that in the first place, but there are these subtle details that tend to creep up the more that we investigate Newton's three laws. And that's really going to be the goal of this video, is we're going to take a deeper look into Newton's three laws. Primarily the first two, but we'll also do a little bit with the third law as well. And we're just going to start to look at more of the details, the mathematical subtleties that come with Newton's three laws. And in doing that, I think we're going to gain a deeper understanding of them. Okay. So hopefully that makes sense. That's going to be the goal of the video. Now, to start things off, I'm going to just draw something right here. And admittedly, my drawing skills aren't the best, so I'm just going to take some time to draw it out, and then we're going to use this picture to start unpacking Newton's three laws. Okay, so this is my attempt at drawing what's supposed to be a table lying on the ground, or laying fixed on the ground. So this top thing here is the table. This bottom plane looking thing here is supposed to be the ground. Okay. Now, what we have here physically is a table that's just kind of standing still. It's not moving, it's just stationary on the ground. A way of generalizing this is that we can think of this table as a particle, because again, we only care about the position of something in order to refer to it as a particle. So this table has a position, it's right here, so we can call it a particle. And because the table is not moving, we can say that this is an instance of a particle at rest. Okay. So just getting used to kind of the generalized terminology that shows up a lot in physics here. Now, what I want to do is I want to just start by drawing some things that go into this picture. It seems like there's not a whole lot going on here. The table's just standing still, right? But I'm just going to draw some things that go into why this table is standing still. And in doing that, we're going to learn something about Newton's first law. Okay. So the first thing is that there's a concept that we're going to talk in much more detail about in the next section, but it turns out that everything on Earth, as long as it has a mass, is going to be influenced by gravity. And hopefully this is familiar, right? If you take an object and you were to drop it, or let it go, I should say, it is going to fall down towards Earth due to gravity. And that's just because the object, or whatever your particle is, whatever your thing is, it has mass associated with it. Now this table has mass right here. We could give it whatever mass we want. We could call it 10 pounds, 10 kilograms, 100 kilograms. The mass itself doesn't matter a whole lot. But the main idea is that it has mass. And because it has mass, it is going to experience a force from gravity on it. And it's going to be down towards the center of the Earth. So what I'm going to do is I'm just going to draw an arrow that is indicating that there is gravity that is acting on this table right here. So I can draw a downwards arrow like this and say that this downwards arrow represents the force due to gravity. Now I'm just writing F sub gravity for the force due to gravity. And for now, we're not going to worry about any of the details in how you would calculate this force. So we're not going to look at how strong it is, what are the components that go into the force. All we're saying is that there's some force and gravity is responsible for that force. Okay. So hopefully that makes sense. That's the first part of this picture here. Now to draw out the second part of this picture, we're going to actually go just quickly to Newton's third law. If you remember, we said that every action has an equal and opposite reaction. And the example that we gave in the last video is that if my hand is pushing on the board equally is pushing back on my hand in the opposite direction. So we can apply that here as well. Right now, the table is pushing down on the ground because of gravity. It's causing the table to get pushed down on the ground, but because of Newton's third law, the ground is going to also push up on the table. So the table doesn't just experience a force from gravity, it also experiences a force because the ground is pushing up on the table. So what I'm going to do now is I'm just going to draw an arrow going upwards, saying that there is also a force, F, due to the ground pushing up on the table. And again, for now, we're not going to worry about the details about how strong this is, how you go into calculating it. The only thing that matters is that you have a force due to gravity and a force from the ground. So there are two total forces acting on this table right here, but still the overall table is standing, it's at rest, it's stationary. Okay. I might be saying, okay, sure, but what I want us to take away from this is I want us to go back to Newton's first law and let's reread it again to make sure that we don't fall victim to this misconception here. It says that a body is going to remain at rest, which is what the table's doing, or it's going to move uniformly in a straight line, so one of those two things, unless it's acted on by a force. Okay. Now, if we're not careful there, it might seem like it's saying it's going to do this or it's going to do this. One of those two scenarios unless it's acted on by a force. But if it is acted on by a force, then these two things aren't going to apply, right? So, and it's that second part that's not quite the case, okay? And this is a good example of it, because this is an instance where the particle, the table, is at rest. So it's in this first of two scenarios right here, but it is acted on by a force. It's actually acted on by multiple forces. It's acted on by the force of gravity and the force from the ground. So even though there are forces on this table, it still falls into one of these two categories. The same thing can be applied with an object moving uniformly in a straight line. You could, in fact, have forces acting on it while it's still moving uniformly in a straight line. So what's going on here? What do we really mean when we're saying unless acted on by a force? Because it seems like this example kind of contradicts what we're saying right here, right? And this is one of the first details that I didn't want to get into in the last video, but we're going to get into now. When we say acted on by a force, what we really mean, let me not put quotes on it, this is what we really mean. When we say a force, what we're actually referring to is a non-zero net force. Okay? A non-zero net force. So let's reread Newton's first law, make sure that we have it correct. It says, a body is going to either remain at rest or moves uniformly in a straight line unless it's acted on by a non-zero net force. And that's how we should read it. Okay. Now the next question is, well, what is a non-zero net force? It looks just like force, but we put some words in front of it, right? So the first part of this is the net force. Net in physics is just a way of saying what is the total force acting on an object. So if the total force of all of the forces added up together on an object equate to not zero, then it's going to deviate from one of these two scenarios. But in this instance, and what we're going to see in a second here is we're going to calculate the net force of this, the net force on this table right here. And we're going to see that the net force is zero. So you could have an instance where the net force is zero, and then one of these two scenarios is still going to apply. But it's when your net force becomes non-zero that the particle or the object starts to deviate from one of these two cases. Okay. So let's go about calculating the net force on this table right here. So whenever we refer to the net force, that is simply the sum over I of all of the individual forces F of I acting on our object. So this is the generalized notation, sum over I of F of I. But in the case of this table, our sum just goes from 1 to 2. We have two forces acting on the table. The first force is, do the up arrow one, the force due to the ground. So in this case, we have the force due to the ground. And then we also have the force due to gravity. So the force due to gravity. So the sum of these two terms right here is what we call the net force acting on the table. Now, to understand how we could go about calculating this, we can actually come up with an expression for this, a numerical expression, even though we don't know the details of these two forces. The way that we can do that is by going to Newton's third law. We said that if the table exerts a force on the ground, then the ground is going to exert the force on a table, and it's going to be equal and opposite in its direction. Okay? And the equal and opposite part is important right here. So in this, I'm still going to have my force of gravity. This is going to be the force of the table going down on the ground. So I'm still going to have F sub gravity right here. So we have F sub gravity. But then for F ground, without knowing the specifics of it, we know that from Newton's third law, this needs to be equal to this and opposite in its direction. Okay? So we know that the force on the ground, because the object is standing still, is going to be negative the force of gravity. Okay? The fact that the force of ground is equal to the force of gravity in magnitude shows that it's equal. And the minus sign is what indicates that it's going in the opposite direction. If gravity is pointing down, the force from the ground is pointing up. Okay? So this is the net force acting on the table, and then we can see that regardless of what F sub gravity is, we have the negative of that plus itself, and that needs to be 0. So this is an instance where the net forces acting on this system right here are 0. And because we have a 0 net force, then the body is going to remain either at rest or it'll move uniformly in a straight line. Okay. If one of these two were larger than the other, that would cause the table to accelerate, and then that's where Newton's first law would no longer apply. Okay. But hopefully that makes sense. When we refer to this as a force, we're really referring to a non-zero net force. All right. So that's kind of the first subtlety that's going to come with this. The next thing that I'm going to do is I'm just going to erase this right here, and we're going to start to draw out some reference frames. And we're going to see how does this picture kind of change when working in different reference frames, and go from there. Okay, so what we've determined so far is that even though there are forces acting on this table right here, and in general, forces can act on a particle that's at rest or moving uniformly in a straight line, it's the fact that the net force, the sum of the forces, adds up to 0, and that's why it can move either. It can either stay at rest or move uniformly in a straight line. Okay. Now, the next thing that we're going to do, we're going to take a look at the idea of a reference frame, because we talked about that in the last video. This particle, this table, has a position associated with it. It's right there. So what I can do is I can say, all right, maybe that is the given position in this reference frame, and this is my set of coordinate axes to say this is the origin, and then maybe the position of the table is over here, right? And this is going to be my reference frame S. Now, say, okay, sure. We've assigned a set of, I guess, 2D coordinates because we're on a whiteboard. Or we could say 3D coordinates. I guess this is a 3D table, right? So this is in 3D space. and this table here has a 3D position relative to this origin, right? Now, what I'm going to do is I'm going to not just draw out this one reference frame, S. I'm going to draw out another reference frame. This is what we'll usually do when we're drawing reference frames, but again, what this really means is this is another set of coordinates. Hopefully we can see these are supposed to be kind of these arrows, where this is the origin, right? And we're in 3D space right here. That's what I'm doing when I'm trying to draw out a reference frame. This reference frame is going to be called S prime. And not only is S prime shifted relative to S, meaning that the origin of S prime here is shifted relative to the origin of S right here, I'm going to add an additional constraint to S prime. I'm going to say that, as if there's not enough arrows already on here, I'm going to say that this frame, even though I can't draw it physically, we're going to pretend that this reference frame is rotating. So you can hopefully imagine, I'm going to do my best. I have 2 of the 3 axes right here. And as time progresses in this frame S prime, the frame is, well, I guess it's doing this, right? It is rotating consistently in space. All right. So hopefully we can imagine that. Now let's for a moment suppose that out of these 2 reference frames, we're for now existing in reference frame S. So we're right here, we're at the origin, and we're standing still. And looking at this, we're saying, okay, the table is at a position of right here, wherever that is. And we just showed in the previous whiteboard that the net forces acting on the table add up to 0. So because the net forces on the table add up to 0, this particle should either be at rest or moving uniformly in a straight line. And it's at rest, so we say, okay, Newton's first law checks out there. Okay. This is if we're in the reference frame S. I'm supposed to be standing in the reference frame S now, right? Now, let's suppose we have a different scenario. We're not standing in the reference frame S, we're standing in this reference frame S prime. Now, in order to stand in the reference frame S prime, this would be like if we placed ourselves and put ourselves at the origin, and we would just ask, what would we see? Okay. Maybe let's even draw us. This is us right here. We're kind of happy. I try to draw a bigger smiley face, but this is us here. We're at the origin, and because S prime is rotating, this is what I would be looking at if I am in frame S prime. I am quite literally doing this if I am in frame S prime. Now, let's ask ourselves, I don't know how long I should be doing this and how dizzy I'm going to get, but let's ask, what does the table look like to me as I am rotating in frame S prime? And if I were to just pause my rotation right now, I would say that, oh, the table looks like it's over to the right of me. I'm looking forward and the table's at my right, right? But if I were to continue rotating, like what is specified here in S prime, eventually I'm going to rotate over this way, and now it looks like if I'm looking straight ahead, now it looks like the table's to my left. It was to my right over here, but now it's to my left over here. So the idea is that if I am in this rotating reference frame, S prime, now it looks like, to me, when I'm doing this, it looks like the table's rotating, okay? Now, you might be saying for a second, well, obviously the table's standing still and you, and me, is rotating. But if I'm in this frame right here, I can only look at what I see, right? And that's what I see. In one instance, the table's to my right, and then it slowly moves over to my left. It looks like the table is rotating around me if I'm in frame S prime, okay? Now, hopefully that wasn't too boring, watching me just spin around for however many seconds that was. But the big idea that I want us to get across in that instance is that when we're in frame S prime, we've already established that the net forces on this table are 0. Just because I'm rotating over here, that doesn't do anything to the table. The table's still just where it is, right? So this is an instance where the net forces on the table are 0, but because of the reference frame that I'm in, it looks like the table's rotating, okay? And if we remember from the last video, we talked about different types of acceleration. Acceleration could be speeding up, could be slowing down, or it could be changing its direction. This table, if I'm in frame S prime, because I'm rotating, this table is going to be changing its position. The table is rotating, and hence, when I'm in S prime, it looks like the table is accelerating because it's changing its direction, even though we've already established the net forces on the table were 0. So now, the only thing that I had to do is I had to just start spinning like this in this new frame S prime. And now all of a sudden it looks like Newton's first law doesn't hold for me in this frame, right? Whereas it did hold in this frame. Because here, we see that it still has a 0 net force, but it's not at rest now, and it's not moving uniformly in a straight line. It is rotating according to me. Now, the obvious sort of thing that you could be saying here, and I need to stop spinning for my own sake, is well, isn't it obvious that the table's at rest and that it's me that's doing the spinning? Isn't that obvious? And we might initially want to say, yes, that is obviously what's going on, okay? But what I want to do is let's just take a moment here to think about how what is considered obvious might not actually be so obvious. And here's what I mean. Here we have a table. Let's say here I have an eraser. The eraser right now, and I'm not spinning. Now, to me it looks like I'm spinning because I'm dizzy, but I'm not spinning. So right now, if I'm not spinning, it looks like this eraser is at rest. Hopefully, and I'm asking you as the viewer, would this eraser here be at rest? Or is this eraser spinning? Right? And we might say, well, obviously, we're doing our best to keep this still here. The eraser is at rest. It's not accelerating. It's not rotating at all, like we were over there. But keep in mind, I'm doing this on planet Earth, and you are most likely watching this on planet Earth. And planet Earth is inherently rotating as it orbits around the sun. So if we were to no longer just imagine now that we're on Earth, let's imagine for a second, and we're drawing a whole bunch of things now, but let's imagine that this is the sun right here. We're looking in a frame, whatever this new frame is, where the sun is at rest. Sun's just chilling right there. Now all of a sudden the Earth is rotating as it orbits around the sun. So even though all of us would agree that the eraser seems like it's at rest, just from the fact that we're on planet Earth, Earth itself is rotating. Earth is doing what S prime is doing. So then it becomes, okay, well, what does it mean to even be at rest? And you see how it can get kind of complicated, right? It can get confusing pretty quickly. And I don't want us to get too confused here, but I do want us to make sure that we see this idea that by picking this type of reference frame, a rotating reference frame, we have now seen an instance where it looks like the table's accelerating because it's rotating, despite the fact that it has a net force adding up to 0. So what's going on? Does Newton's first law and second law, do Newton's laws break down all of a sudden? Do they no longer work? Because we found a counterexample here with a spinning reference frame. And the answer is no, thankfully. Newton's laws still are upheld, but there's another caveat that we didn't introduce last time. Newton's laws inherently require us to work in what's called an inertial reference frame. So that's going to be a big idea. I'm going to erase the board. We're going to write out the definition for an inertial reference frame and then spend some time unpacking that. Okay, so we have the definition up here for an inertial reference frame. And then right below this, I just rewrote Newton's first law again, just so we could have as a reference, I guess. No pun intended, of course. Let's first go through the definition here. It says that an inertial reference frame is a frame of reference where the frame itself is not accelerating. Okay. So this is talking about the inherent coordinate system that we are working in. If we were to go back to the example where we had the stationary, just a table that was just standing still, right? Try to draw it really quickly. We have our, not sure if any of the drawings are good. This probably isn't one of the better ones, but this is supposed to be the table, right? And then we had our first reference frame, which we called S, and it was just staying fixed. And then we had another reference frame, S prime, and we said that S prime was inherently rotating by some amount, okay? So if we were to go back to this definition here for an inertial reference frame, we could ask which one of these is inertial and which one is non-inertial. So because S is by itself fixed, it's not moving, we would say that S is an inertial reference frame. And because S prime is rotating, it is inherently changing its direction, so we would say that S prime is a non-inertial reference frame, okay? So that's how we can classify the difference between these two right here. And this is important because when it comes to talking about Newton's laws, it turns out that Newton's laws work under the assumption that you're working in an inertial reference frame, okay? So this is another one of these subtle points that was not mentioned in the previous video, but it's an important one, right? And we saw that it was important here too, right? Because in this inertial reference frame, S, the fixed one, we looked at the net force on this table right here. We said, what is the net force on this? And we said that it was 0, right? Whereas over here, the net force was still 0. There were still only these two, the force of gravity and the force from the ground acting on this table. But here it looked like all of a sudden now the table is rotating, right? Because we're in this frame S prime. So it looked like Newton's laws did not get upheld here. And it turns out, well, they didn't because this was a non-inertial reference frame, whereas this was an inertial reference frame, okay? Now, something you might be wondering, this is something I was wondering when I was first learning about inertial reference frames, is we're saying that this one is fixed right here and this one's rotating. So this is the nice inertial case, and this is kind of the more complicated non-inertial case. But let's just suppose for a second that we're standing in this frame S prime here. We have our same guy, and we're in S prime, and we're just rotating in S prime. Maybe though it's not, let's say that this is us here in S prime, and let's suppose that it's not so obvious that we're rotating. Maybe it looks like we're standing still and everything else is rotating around us. For example, right now it probably looks like, I guess you can't see this room, but it looks like most of this room is standing fixed while I am the person that's rotating counterclockwise. But when I'm doing this, I could also say that maybe it looks like I'm the one that's fixed and the entire room around me is rotating clockwise. So what I'm trying to say is I could be in this frame and it might look like I'm the one that's standing still. And now all of a sudden S is rotating clockwise relative to me. Even though we said that this one's fixed and this one's rotating counterclockwise relative to this one. So which one is right? Because I could say I'm standing still here and this one's rotating, but equally I could say I'm standing still here and this one's rotating. So according to here, it might seem like now this is the inertial reference frame and this is the non-inertial one, right? And it can be a little bit confusing. And in order to, I think, get a better understanding of, well, which one is really the inertial one, turns out is this one. This is in fact the inertial one. We need to go beyond just looking at one frame relative to another. Here it looks like we're standing still, this one's rotating counterclockwise. Here it could look like we're standing still and this one's rotating just clockwise. So how do we know that this one's inertial, this one's non-inertial? And what we can do is we can look at the sum, or we can look at the net forces acting on an object. Notice, and we tried to make this clear in the previous whiteboard, whether we were standing still right here in frame S, or we're rotating over here in frame S prime, what we're doing has no influence on the table that's standing over here, right? The table is just standing still. It doesn't care about us. It still has a force from gravity going down and the force from the ground going up. And that's not changing at all. So the idea is that, and this is what's common between these two frames right here. Regardless of what frame we're looking in, this object still has two forces acting on it, and we calculated it roughly and showed that the net force on the table was 0. So another way that you can determine which of these in fact is the inertial reference frame, you can say that if the sum of your forces is 0, so if your net force is 0, that implies that your acceleration is 0. If this statement right here is true, then you are in fact in an inertial reference frame. Okay. Let's go through this logic through both of these so we can clearly understand why S is in fact the inertial one and S prime is not the inertial one. In frame S, there were two forces acting on the table, gravity and the ground. So the net force was 0. And then that should imply that the acceleration is 0. Well, if we're just in this frame S and we're standing still, we look at the table, it's also standing still. We see the net forces are 0, therefore, and we see the acceleration is 0, therefore this statement right here is true. And thus, we would say that S, we would be in an inertial reference frame. Okay. Now let's go over to this example of S prime here. If we're in S prime and we're rotating, I'm going to stop rotating for my own sake. There are still two forces acting on the table. We got gravity going down, the force from the ground going up, so that sum of the net forces is 0. But does that imply then that the acceleration is 0 according to us in this frame? And that's where we determined that was not the case. Even though this was true, this turned out to be false. Because when we were rotating, it looks like the table's now rotating, right? So in the non-inertial case, the sum of the net force, or the net force could be 0, but we could still get a non-zero acceleration. And because this sort of if-then condition didn't get upheld in the case of S prime, that's why we determined that objectively S prime is the the non-inertial frame, and S is the inertial one. Okay. So hopefully this makes sense. Okay. This is how we can determine if a frame is inertial or not, and it's important because that's when Newton's laws are upheld. Now we're going to go through one more subtle point, but I think this is an important one, and this is where we go back to what we wrote down here for Newton's first law. Let's just read it real quick again. It says that a body or some particle or object remains at rest or moves uniformly in a straight line unless acted on by a non-zero net force. Okay. Now, this is the behavior that gets upheld if we're in a inertial reference frame. So what wasn't mentioned when we first wrote out Newton's laws is that this statement right here is true under the assumption that you're working in an inertial reference frame. You need an inertial reference frame in order for this to even be possible. Let's look at the converse case. In the non-inertial reference frame, this simply was not possible, right? We had the sum of the net, we had the net force adding up to zero, but the particle was not at rest and it was not moving uniformly in a straight line. It was rotating. It looks like it's rotating, right? So this inherently relies on the fact that you have an inertial reference frame to even work in the first place. So another way of writing Newton's first law, and you'll see this occasionally, David Tong does it in his notes, and I'm glad that he does, is rather than just thinking of Newton's first law as this special case of Newton's second law, another way of writing it is, well let me write it out real quickly, and then we'll just quickly talk about it. Okay. Okay, so Newton's first law revised. Another way of saying this is that inertial reference frames exist. And it's kind of like oh, okay, interesting. It's such a compact statement, but hopefully it makes sense though too, right? And this is an inherent requirement in order for this statement, this longer statement, to be true within the first place. And that's what we've spent a lot of time trying to show so far, right? And the same thing with Newton's second law and Newton's third law. Those laws have the properties that they do under the assumption that an inertial reference frame exists. So I like to write this because I think it kind of makes Newton's laws more complete. Newton's first law we can think of as talking about the idea of an inertial reference frame in the first place. Newton's second law talks about forces and accelerations, whether that acceleration is zero or non-zero. It can encompass both cases, and then Newton's third law is still upheld as well. Okay, so kind of a lot of these subtle details, but hopefully all of what we've been talking about so far makes sense. What I'm going to do now is we're going to take a slightly deeper dive into inertial reference frames. The reason, again, is because they're so important. Newton's laws work under the assumption that we're working in these things in the first place. We drew out an example reference frame, which was inertial. That was frame S. But we could ask ourselves, is frame S, the one that we drew, the only inertial reference frame? And you might be able to imagine, probably not, right? If we drew a frame S right here, and it was still, I could also draw a frame S prime here that's also still. This would also be an example of an inertial reference frame. So we can see that there's not just one inertial reference frame. It's not like there's only one sort of origin that we can pick, one coordinate system we can pick where Newton's laws work. So then the question becomes, okay, well, if there are multiple of these inertial reference frames, how can we find more or less all of them? And more importantly, how can we transform between the two? If we're going from an S to an S prime, how do we guarantee that Newton's laws are upheld in the process? So we're going to go through those ideas next. Okay, so we have something here. It's a set of transformations called Galilean transformations. Let's first just go through these transformations to understand their properties. Then we're going to relate their significance back to inertial reference frames. So Galilean transformations by themselves are a series of transformations. And the first sort of class of Galilean transformations are translations in space. So with each of these three instances right here, we're looking at a starting coordinate system, x, and converting to a new coordinate system, x prime. This would be like going from one reference frame s to another reference frame s prime. Okay. One type of way which we can relate reference frames is by translations. You can have x prime, your prime coordinates equaling the unprimed coordinates plus some constant vector a. This was the example that I think we were talking about at the end of the last whiteboard, where if we have some fixed reference frame here, s, and it's just standing stationary, we have another one over here that is also stationary, s prime. We would say that s and s prime are related to each other by a translation space. Then moving on to rotations, we would say that the primed coordinates, so the primed reference frame, x prime, is related to the unprimed reference frame by a rotation matrix R. It would satisfy R transpose R equals the identity. And I'm aware of, and hopefully you're aware of the fact that this condition right here, where the transpose of a matrix times the matrix itself equaling the identity, this is the condition for an orthogonal matrix. And orthogonal matrices could be rotational matrices or reflection matrices as well. Galilean transformations are primarily concerned with rotation matrices. So in addition to this, we could also say that we would have that the determinant of this matrix here is 1, as opposed to -1 if it was a reflection. But in the general case, you would have this, it would account for both rotations and reflections. Okay. So that's the second type of way which we can relate these two coordinates, two frames of reference. And the final one is through a boost, where the primed reference frame is equal to the unprimed reference frame plus this additional factor. This additional factor now is no longer a constant like it was with the translations case, but it's equal to a product of two things, v times t, where v is a constant velocity vector. So this is a constant vector v, but this vector v is getting scaled up by a parameter t, which stands for time. And this would be the idea where if you had s that was stationary, s prime maybe moving to the right by, 5 meters per second. It has a velocity of 5 meters per second to the right. We would still say that s and s prime are related to each other. They're related by a boost, where the constant velocity vector in this case would be 5, okay, 5 meters per second. So these are the transformations in themselves, and we kind of mentioned it in the previous whiteboard, but there's not a single inertial reference frame. And it turns out that these three classes of transformations are how we can go from one inertial reference frame to another. And this is why we care about these so much. Okay. Now, one thing that you might be wondering is we're saying that these rotation matrices, right, or these transformations that are determined by rotations allow us to go from one inertial reference frame to another inertial reference frame. But what about this example that we've been going back to a couple times now with that table where we had one frame S and then another frame S prime which was rotating? We said that S was inertial, S prime was non-inertial, but isn't S prime related to S by a rotation if it's rotating? And the answer is, well, the fact that it is rotating, it is currently in the process of rotating, is what makes it non-inertial. If we were to just perform a rotation at one point, but then fix it, so then maybe this is what S looks like, and then maybe S prime just looks something like this, where we can imagine taking this frame right here and just rotating it counterclockwise by an angle theta, like this. But now that once we've rotated by an angle theta, we just left it alone. So this is standing still, now this is standing still. These would be related by a rotation matrix, and this would be an inertial reference frame, and this would also be an inertial reference frame. Okay, so that's kind of the distinction between a rotation as a type of transformation versus what we saw on the previous whiteboard, because I can see how that could be confusing. Okay. So these are the set of transformations that take us from one inertial reference frame to another. And it turns out that we can use these transformations along with a general principle to tell us a lot of interesting ideas about our universe. I'm going to write out this principle. It's called the principle of relativity, and then we're going to go through that together. Okay, so we talked about the set of Galilean transformations, and now we have the principle of relativity here, which states that the laws of physics are going to be the same in all inertial reference frames. Okay? And essentially what that says is that the laws of physics are going to be the same regardless of where you put your origin, how you orient your origin, and the relative boost that you are at, or what your speed is, your velocity is relative to something else. Okay. Now let's make sure that we understand this here before moving on to Newton's second law. All of what we've been talking about is Newton's first law, and kind of the subtleties of that. Let's finish that discussion before moving on. So the idea is that if the laws of physics are going to be the same between inertial reference frames, let's start with translations. That means that Newton's laws are going to be upheld whether we're in frame X or frame S or frame S prime with coordinates X and X prime respectively. This tells us that there is no special location, no special position in the universe. Unfortunately for us, this means we are not the center of the universe, we are not considered any special point within the universe. There's nothing special about planet Earth being at the center, or the sun being at the center, or the Milky Way being at the center. There's just one position relative to another, and the laws of physics are going to be upheld regardless of where you put your origin. As for rotations, we kind of saw this in the previous whiteboard, right? Where if we have one frame S and then another frame S prime where it's rotated by some angle theta, it doesn't matter which way we are oriented. The laws of physics are going to be the same here as they are here, so there's no objective special direction as being the direction up or the direction forward or anything like that. No matter which way you orient yourself, as long as you are fixed at a given orientation, the laws of physics are going to remain the same. And then finally here for boosts, what this seems like is that regardless of what speed you're moving at relative to something else, the laws of physics will not change. Now what I really should do with this principle of relativity is I should put an asterisk on this. This might seem that if we have a frame S, maybe that's standing still relative to a frame S prime, which is moving at, whether it's 5 meters per second, 10 meters per second, 100 meters per second, 1 billion meters per second, whatever it happens to be. It would seem that as long as you're moving at a constant velocity, then the laws of physics here are going to be the same as the laws of physics here. Now, I put an asterisk on this because it turns out that we might be initially saying that there's no special speed in the universe, but it turns out, well, there's one special speed in the universe, and that's the speed of light. It's the fastest speed that anything can travel at within the universe, and we're going to talk about it later on in the video series when we get to Einstein's theory of special relativity. Turns out the speed of light is in fact a special speed. And the laws of physics are not quite the same when you get to speeds close to the speed of light. They start to deviate from Newton's laws a little bit. But for the most part, for most speeds that we see in everyday life, there's no special speed where the laws of physics are quote unquote better. They're all going to work the same. Okay. So hopefully all that makes sense, and kind of gives us a nice idea about how general the laws of physics are. And also, this is very useful too, right? Because if you're doing astrophysics, for example, and you're studying objects way out and on the other side of the universe, very far away from us, as long as that object is in a reference frame that is also an inertial reference frame, and we are in an inertial reference frame, then we can assume the laws of physics way out there are going to be the same as the laws of physics here. So this gives us a lot of generality with the laws that we're working with. Okay. Now, the final thing that I want to mention, this talks about translations in space, rotations in space, and moving at constant velocities. Notice that out of these three sets of transformations right here, there's nothing that talks about an acceleration. And hopefully that makes sense, right? X prime should not be accelerating relative to x, because if x is inertial, if we want to get to another inertial reference frame, it should not be accelerating, right? So almost purposefully, by definition, we haven't included any sort of accelerations in this set of Galilean transformations. And that also tells us something about the universe. It tells us that when it comes to looking at objects in the universe, while there's no special position, no special orientation, and no special speed, when it comes to accelerations, you don't need to worry about whether you are accelerating relative to something else or not. And we kind of saw this in the example where we had the table, right? We had the table and we had our frame S prime, which was rotating. This frame was an accelerating reference frame, and all of a sudden Newton's laws broke down in this frame where they did not break down in the stationary frame S. So what this tells us then is that as long as you are, if you are accelerating, then Newton's laws are not going to be working how you would typically expect them to be working. Or if you're working in if you're working in a reference frame which is accelerating, that will happen. Okay. Worry if I'm over-explaining that, but hopefully that makes sense. Okay. Now, this is enough about Newton's first law. We're going to finish up the video kind of going into a little bit more specifics about Newton's second law, and we'll probably call it at that point. Okay, so now to finish out the video, we're just going to kind of go through in a little bit more detail Newton's second law, and we'll call it there. Just to reiterate what this is, because we've been talking a lot about inertial reference frames now. It says that when a force is exerted on a particle, the particle accelerates, and it's going to accelerate at a rate proportional to the force acting on it. So, like what we mentioned kind of at the beginning of the video, if there is a force acting on a particle, the particle will accelerate at a rate proportional to the force acting on it. That's what this law says so far, but we're going to take this a step further. The first thing that we can do, is we hopefully remember that from the previous video that the acceleration of a particle is just the second time derivative of the particle's position. So this is inherently a vector quantity, and that means this is also a vector quantity, right? And hopefully that makes sense. You're accelerating in vector quantities just indicate a magnitude and a direction. So you're accelerating in a given direction, or a force is being applied in a direction. So these are both vector quantities right here. But what we'd like to do is we'd like to make this stronger than just a proportionality. We'd like to turn this into an actual equation. What we can do is we can relate these two if we introduce a constant of proportionality factor. That's what we're going to do right now. So it turns out that the force on a particle is equal to its acceleration, and it's related by this parameter m, which happens to be the mass of a particle. Okay. So this is kind of one of the most famous laws in physics. This is the F equals ma law. You hear often if you read physics material. And this is Newton's second law, or this is one way of writing Newton's second law, relating the force, acceleration, and the mass kind of all together in one equation. Now, what we would like to do is we would like to not just relate these three variables in this way right here, but we'd also like to remember from our knowledge of calculus in the last video that the acceleration is the second time derivative, right? So I'm going to take this right-hand side, I'm going to rewrite it on the left-hand side, and rather than writing m times a, I'm going to rewrite this as m times d squared r, where r is the position vector, times dt squared, like this. I could have also written d squared x dt squared, same thing, but that's what I'm referring to. This is m times the acceleration, and then on the right-hand side, rather than just writing out this force as a vector quantity, we can say that in general, forces will depend on your position, maybe your velocity, r dot, and also time. So this is inherently a vector function. And now what we see is that we don't just have an equation relating a particle's mass, how much it accelerates, and the force acting on it, but we now have a second order differential equation, second order derivative, and then some right-hand side that gets solved. And the main thing that we want to take out of Newton's second law, there's not too much beyond this other than the fact that because this is a second order differential equation, that means that we're going to need two sets of conditions to find a precise solution for it, right? Given that it's second order. The common instance that we see in a differential equations class, if we're taking differential equations, is we would say, okay, well, what's the position at time 0? That might be something. And what's also maybe the velocity at time 0? If those two conditions are specified, then we would have, we could get our exact solution to the differential equation. But I just want to point out that this is not the only way that we can obtain two conditions for this differential equation right here. Another way of doing this, and we're going to see this often in this course, which is why I bring it up, is you could also have either the position or the velocity at two separate points in time. So another set of conditions that you'll see often is you might see the position of the particle at some time t1, doesn't necessarily need to be 0, and you might also see the same position of the particle, not the velocity, but the position of the particle at another time t2. And if you know the particle's position at two instances in time, that is an equivalent way of saying that you have two conditions that can allow you to solve for the full solution to this equation right here. Okay. So hopefully that makes sense. Main takeaways is that it's a second order ODE, and because it's a second order differential equation, you need two sets of conditions to fully solve for it, right? Now, one final thing that we're going to introduce, just because this comes up in the way that we formulate Newton's second law. There's another way which we can express Newton's second law, in not necessarily in terms of position, but in terms of a new quantity, which we're going to call this vector p, okay? Now, before writing out this vector p, I'm just going to manipulate this right-hand side slightly. So rather than writing this as m times the second derivative of the position, I could also write this as m times the first derivative of the velocity, right? M times dr dot dt equals our same right-hand side, right? And hopefully that makes sense, right? Because we said that r dot was just dr dt, like this. So just rewriting the second derivative as a first derivative like this. Now what I'm going to do too is I'm just going to bring this, even though m here is a scalar quantity, just the particle's mass, how much mass it has, that doesn't change. It's the scalar quantity. I'm going to bring it inside the derivative. This is a constant, it's usually a constant, so we can typically bring it inside the derivative. And if we do that, we're going to get d times m r dot dt equals our right-hand side, f as a function of r dot, and t, like this. So what we now see is that the first derivative right here of this quantity, mr dot, is equal to the right-hand side. And this quantity here in parentheses is what we're going to call this vector p, and p is known as the momentum of the particle. So we're introducing a new quantity that shows up all the time in physics. P is referred to as the momentum. The momentum of a particle is defined as its mass times its velocity. So the product of m times r dot, the derivative of the position. Okay. We might be asking, why is it p if it stands for momentum? Why isn't it m? Well, we already have mass for m. And I think I think the origins of momentum come from, I'll say it's Latin, and the Latin word for push begins with a P, or it's something like that. Don't quote me on that, but there's a reason why momentum is called P, and it has something to do with those along those lines. So this is this new quantity, momentum, which is just the mass times the velocity of a particle, and we're going to see momentum a lot throughout this video series and physics video series in general. They deal with momentum all the time. So really quickly, just to finish off the video, I want to give us a good conceptual understanding of what momentum is, how we can think of momentum. This is its definition right here. But how can we conceptualize momentum? And then finally, just incorporate momentum back into this equation. So how to conceptualize momentum? The momentum of an object conceptually, intuitively, refers to how difficult it is to stop that object from moving, how difficult it would be to slow that object down. And let me give you two separate instances. Let's say, for example, because momentum is a product of two things. It's a product of the mass times the velocity. Maybe to make this a little more clear, I'll just write m times v, where v is just the time derivative of position, right? There are essentially two ways which we could make this momentum vector p a big vector, right? Have a large magnitude. One way is if we make the mass big, and another way is if we make the velocity big. Let's look at the case where we have a big M, so big M and then little v, okay? This is one case, and then the other case is where we have a little m, and then a big V. As long as this big is sufficient enough to make the momentum big, then both of these cases would result in an object having a large momentum and hence being very difficult to slow down, to stop. For an example, an object with a big M and a little v, that would be an object that has a lot of mass but is moving kind of slowly. So an example would be like a slowly moving semi-truck, for example. So slowly moving semi-truck. So let's just say that we have a semi-truck that's moving at like 5 miles per hour, or 5 meters per second, or whatever. It's not moving very fast, but if you can imagine this really big truck, just the fact that it has a big mass alone, it doesn't need to be moving very fast to make it difficult to slow down. You can imagine if a semi-truck is even coming at you at 5 miles an hour, if you're trying to push against that semi-truck, it's going to be very difficult to slow that semi-truck down. Why? Because it has a lot of momentum. But why does it have a lot of momentum? Because the mass is really large, even though its velocity is not too big. Okay. So this is one instance of an object which has a big momentum. Another way which you could have a large momentum doesn't have to be a massive object. You could have a really tiny object that's moving very fast. An example, probably the first example that comes to mind is a bullet, right? You can take a bullet and hold it in your hand, and usually bullets aren't too heavy by themselves, so their mass isn't that big. But once bullets are shot out of a gun, they're going to be going at very high velocities. So you can imagine if you tried to stop a bullet, which I don't recommend, it would be very difficult to slow that bullet down. It's possible for a bullet to have the exact same momentum as a slowly moving semi-truck. It's just that the reason why both of their momenta are so large is because different quantities in the product happen to be big, while the other quantities happen to be little or small. Okay. So that's just the general idea with momentum. It just refers to, we can think of it as how difficult it is to stop an object from moving. We can ask too, does the object have to be moving to have momentum? And the answer actually is yes, right? If the object was not moving and if it was at rest, the velocity vector would go to 0, and we just have m times 0. So if we had all of a sudden this slowly moving semi-truck, even if it's moving at 5 miles an hour, 5 meters per second, or whatever set of units we use, that has a really large momentum. But as soon as that truck is stopped, now all of a sudden it goes from being very difficult to slow down. Imagine we're trying to stop a semi-truck to not being difficult at all. Like the truck is just standing still. We don't have to push on it at all to keep it, to slow it down, because it's already standing still. So objects with momentum inherently are going to be moving objects. And that's why we can think of it as how the amount of momentum refers to how difficult it is to slow it down. Okay. Now, the final thing is we've talked a little bit now about momentum. It turns out that you will often see Newton's second law written not in terms of a second order differential equation for the position, but a first order differential equation in terms of the momentum. So this quantity right here, m times r dot, that is the momentum. So one other way of writing Newton's second law is the first derivative of the momentum vector. dp dt is equal to f of r dot, and t. Okay. So these are equivalent conditions right here. And the fact that it's a first order differential equation versus this is a second order differential equation, that tells you in terms of, I guess, how many conditions would be needed to solve it. We'll see that these ideas right here of having second order differential equations versus first order differential equations, the type of differential equation that shows up becomes much more prevalent in the next sort of classical mechanics video series. It would be saved for a later time when discussing Lagrangian formalisms, Hamiltonian formalisms. You start to see how the order of a differential equation really plays into things. We're just starting to see that here. Okay. But yeah, I feel like this is enough for now. We've gone into a lot of detail on Newton's laws and inertial reference frames. All right. So yeah, thanks so much for watching. I'll see you in the next one.